You may have seen this formula and thought, who ever found this? How do you actually find it, and how do you know it actually works? Well, if you haven't seen it, let me just explain. 1 squared is 1 times 1 plus 1, 2 times 1 plus 1 over 6. So when n is 1, you do get 2 times 3, which is 6 over 6. So this does work. And suppose when n is 2, that means the left sum only stops at 1 squared plus 2 squared, which is 5. And indeed, if you plug in 2 on the right side, 2 times 2 plus 1 is 3. 2 times 2 plus 1 is 5, divided by 6. These two cancel, and you just get 5. So indeed, the two sides are equal, and you can try doing this for n equals to 3, 4, 5, and you'll see that this always works. Okay, so let's try to see how one can figure out this formula. And I want to define some sequence of numbers called well, first let's think about S0 as the summation when there's nothing added, and S1 as just 1 squared, and S2 as 1 squared plus 2 squared, and S3 as 1 squared plus 2 squared plus 3 squared. So we're going to define these summation sequences, and eventually you see that there's some recurrence relation you can talk about, which is that anytime you take the two neighboring sequence values and you subtract S3 minus S2, well, these two, if you subtract these two, these will cancel, and you're going to end up with 3 squared, right? The same thing here. If you subtract S4 minus S3, it's going to be 4 squared. So in general, if you take S nth sequence and subtract the one before it, you're going to get n squared. Okay. And then S0 is equal to 0. So we have this recurrence relation with the initial condition. And what I'm about to show you is actually some method that works in general. If you wanted to figure out the summation of the cubes, or fourth powers, or like fifth powers, if you want a general formula for 1 to the 5th, 2 to the 5th, 3 to the 5th, and so on until n to the 5th, you can get the solution in the same process I'm about to show you. It's just that it's going to take a long time. Okay, so first write down this recurrence relation. Just write down what's the difference between the neighboring terms, and the very beginning is 0. And here is where some extra hypothesis comes in. So our hypothesis is that Sn should have one more power than this difference. So the difference is a quadratic function, so Sn must be a cubic function. So a times n cubed plus b times n squared plus c times n plus d. And if you have other ones, like if you're doing n to the 5th power, then you would write down order 6 polynomial, so it's going to have lots of terms. So it's going to be more complicated. But the end result, you're going to get a formula for that if you need one. Okay. So we're going to use this, and well, if the Sn is an cubed plus bn squared plus cn plus d, what is Sn minus 1? Well, that will be a, you're replacing n by n minus 1, so it will be an minus 1 cubed plus b n minus 1 squared plus c times n minus 1 plus d. And because s of 0 is 0, if I plug in 0, I get S0 equals to 0, 0, 0 plus d. So S0 is d, so that has to be 0 because of of this condition. So that's going to go away. And the end result is easy. Now all you have to do is replace Sn by this, replace Sn minus 1 by this, subtract them, and see what a, b, c values are needed in order to get n squared. Okay, so here's what I want. I want a n cubed plus b n squared plus c minus a n minus 1 cubed plus b n minus 1 squared plus c n minus 1. Has to be n squared. Now, you might be still feeling uneasy because I made this assumption that it has to be a cubic function. The way you justify after we get the formula is by using mathematical induction to prove that it is so. But in order to prove something by mathematical induction, you need to know what you're trying to prove. So the statement itself should be coming from this method that I'm just explaining, and then afterwards you can use mathematical induction to prove it. Okay, so let me write some basic, really basic algebra. N minus 1 squared is n squared minus 2n plus 1. And n minus 1 cubed would be n minus 1 times n squared minus 2n plus 1, because it's just n minus 1 times this. And if you FOIL this, you're going to get n cubed minus 3n plus 3n squared plus 3n minus 1. And therefore, if I combine these two, I get a times n cubed minus n minus 1 cubed plus b times n squared minus n minus 1 squared plus c times n minus 1 equals n squared. And this means you're doing n cubed minus this, and since n cubed is common, so these will cancel and all the other ones will have the negative sign because of this minus in front. So you're going to get a times 3n squared minus 3n plus 1 plus b times, this time it will be n squared minus this one, so n squared is common, so you're going to get positive 2n minus 1. Okay, and then c, n minus 1, n cancels, so you just get 1 equals n squared. Now I'm going to multiply these out, and arrange in terms of powers of n. So see, 3a n squared, this is the only n squared term on the left, and then for the power of n, here's what I get. Negative 3a and 2b, so the term with just n to the first power will be this one, and then you have a minus b plus c, a minus b plus c, and then I'm going to write the right side as n squared plus 0n plus 0. And these two sides should be equal as functions of n, right? For whatever n value is, this has to be an identity. And if two sides are an identity, then you would see that 3a has to be 1, and negative 3a plus 2b has to be 0, and a minus b plus c should be 0 also. Okay, so you have a equals to 1/3. Plug that in here, so negative 1 plus 2b equal to 0, so that gives you b equals to 1/2. Plug that in here, and you get c equals to negative a plus b, but negative a is negative 1/3 plus 1/2, b is 1/2, so you get 1/6. Okay, so we figured out what the number should be. We found out that a should be 1/3, and b should be 1/2, and c should be 1/6. That should be the formula for the function, the summation 1 squared plus 2 squared plus 3 squared plus n squared. Now that still doesn't look like our initial formula, which is this one. So let's try to factor this. Note that if I make common denominators, make it as 1/6, this will be 2n cubed plus 3n squared plus n. And I can also factor out an n, which gives you, so this left side is same as this, which is same as that, and this one factors as n plus 1 times 2n plus 1, right? So you end up with the following. So this actually shows that this should work. Now you should still verify that indeed these two sides are equal for n equals to 1, 2, 3, and then rest of it. To actually prove that this is true, you would use the mathematical induction. But to get the formula, you would use this process. The same process can be used for any powers of n, and that's how you do it.